Right, organic second. I could teach it, and then we wouldn't learn any organic. All right, shut up. All right, listen. Listen, our exam is today's the 8th, so we have next week, and then Thanksgiving, and then the following week, and then we'll have our 4th exam. It's the last class day, or the day before the last class day. And then I'll return on the 6th, and we have our final on the 11th. Hey, if you're the kind of person that wants to start looking at the final, not a bad idea. The way I'm going to make the final is comprehensive. It includes the whole semester. The way you prepare for it is you go back and look at the 4 exams that we've had this semester. So you already have 3 of those exams. You can be 3/4 done studying before you even take the 4th exam. Okay? I'll take those questions from those 4 exams. Second, Mackenzie. And I'll change them up. I'll change the numbers in some cases. I'll change the context a little bit. But if it's on those 4 exams, it's fair game for your final exam. Mackenzie? Yeah. The formula sheet, because we're all about being nice here at Nickel. Yeah. No, it's going to be more. It's going to be like 45 questions. But you get 2 hours. Yeah, it's twice the amount of time. All right. Let's see. Last time we worked through this problem, let's look at rotational kinetic energy, and then we'll do some practice problems. All right, so we had talked about kinetic energy. I remember in chapter 5 or whatever, it was important as we were talking about, say, something going up and it goes up and then it comes back down again, that down here it has kinetic energy. At the top it has potential energy. This is called translational kinetic energy. And that is when something's moving in a straight line. Or it doesn't have to be necessarily straight. We'll just say in a straight line. On the other hand, we can have rotational kinetic energy when something's rotating. So like, for example, if this thing is also rotating as it goes up, like this, it has both translational kinetic energy and rotational kinetic energy. So you can also have rotational kinetic energy. And that's just when it's rotating. And remember, we've been making these variable, what's it called, insertions or replacements, if you will. So if we had the kinetic energy was 1/2 mv squared before, you can imagine what you think the kinetic energy is going to be now. It'll be 1/2 not m, but what? I, and then omega squared. So where we had m, we now have moment of inertia, and where we had v, our translational velocity, now we have our angular velocity, our rotational velocity. Our units here are kilogram meter squared. And then our velocity squared is going to be 1/second squared. And so those are the same units as a joule. So our rotational kinetic energy is also measured in joules. It's kilogram meter squared per second squared. This is my moment of inertia, mr squared. This is my speed squared, radians per second squared, or excuse me, radians squared per second squared. I don't write the radians, because radians, not really a unit. Okay, we've been writing it, but it's sort of as a placeholder. And so now my physical units are kilogram meter squared per second squared. So the mass, we've talked about this, but the mass is a measure of an object's inertia. In this translational energy, it's going to be replaced with the moment of inertia. That's I, which is a measure of the object's rotational inertia. And the speed is replaced with the angular speed. The speed v is replaced with the angular speed, omega. So I could ask you a question where I have an object that has both V, like this situation where you have something that's both spinning and moving in a straight line, and ask you what is the total energy. And the total energy in that case would be the kinetic energy rotational plus the kinetic energy translational. That's 1/2 I omega squared plus 1/2 mv squared. By rotating it now has more energy because of that rotation. Our work energy theorem also applies here, and I'll show you some examples of how we'll deal with this in questions, but let me just lay it out. But the work energy theorem is that when you do work on an object, you increase its energy. That is to say that work is equal to a change in energy. Usually we're talking about a change in kinetic energy, but it can also be a change in potential energy like we saw in Chapter 5. But this also applies for rotational motion. All right, remember our definition for work, that work is equal to F times D, right? Our force times our distance. Well, that work in a rotational framework is going to equal to not force, but our angular force, our torque, and not D, but it's going to be theta, torque times theta. So, well, we'll look at an example later where we actually apply this, where if I do torque over, if I apply a torque over an angle theta, I do work on that object. And I increase the energy by that amount of work. That is, that the energy would change by the amount of work that you've done, which is equal to tau times theta. The work that I do applying a torque over a certain angular displacement causes an increase in energy on that object. It makes it spin faster, right? If I apply a torque over an angle theta, it makes it spin faster, gives it more energy. All right, so let's look at this. I have a hoop that's rotating at 10 radians per second, and the radius of the hoop is 1 meter and its mass is 1 kilogram. First, I just want to know what work is required to stop this. So, and then I'll ask a follow-up question or a couple of follow-up questions. So if I want to know how much work is required, I know that the work is equal to my change in energy. And so I want to know what is the change in energy for this object. The change in energy is going to be KE final minus KE initial. I know that initially it has energy, but the final energy is going to be 0. I know that because I'm trying to stop this thing. So KEF, it will come to a rest, and so KEF will be equal to 0. All right. Now I want to figure out what is KEI. That's going to be 1/2 I omega squared. But I don't know what I is. I know what omega is. Omega is 10 radians per second. And so in this problem, I need to first figure out what is I. Well, this is where you would go to your table, because it's a hoop, and we know that hoop is one of those things on that table. You can flip back if you want, and try to pick out the appropriate equation for I for a hoop. So you might recall the hoop, we actually derived that with calculus. I for the hoop is mr squared. It looks the same as the equation that we use for the basic definition for particles, right? Remember, if we had a collection of particles, the moment of inertia was also mr squared, but it's different too. So we're looking at the mass of the object times the radius of the object. This isn't the collection of particles, it's a different equation. So I have 1 kilogram times 1 meter, that's squared. That's equal to 1 kilogram meter squared. All right, so my moment of inertia is 1. So now I can find out what is my kinetic energy. That's 1 kilogram meter squared times 10 radians per second. That's squared. Be very clear that your units have to be in radians. Anytime that I'm actually building units, that is, that I'm building up SI units within an equation to produce another SI unit, which would be joules in this case, your angle always has to be in radians. It's really only when you're using those kinematics equations does it not really matter. So this is going to be half of 100, which is 50 joules. So the answer here is that I have to do 50 joules of work. I actually have to do negative 50 joules of work in order to stop this hoop. Why negative? Is it like in the clockwise direction or something? What does the negative mean? What does that negative mean when I'm thinking about the work? Is what now? Okay, yes, all of those things are correct. You're in the opposite direction of omega, and then also that you're taking away energy. But that's really what I'm trying to get at, is that if I have a negative work here, it means I'm taking away energy from that object and causing it to stop. Okay, that's what the negative means. All right, let's say that I apply a force of a half a Newton to stop the wheel or the hoop. Okay? I apply a force of a half a Newton. How many revolutions does it spin? Before stopping. How many revolutions does the hoop spin before stopping? Now I know how much work needs to be done. I got to do 50 joules of work, or really negative 50 because I'm taking that away. So I apply a force of a half a Newton, and we're going to assume that that force is applied, if this is my hoop, that my force is applied at an angle that's perpendicular to the hoop, because that gives you maximum torque. So if I apply a force of a half a Newton, how many revolutions is it going to go through before it stops? It's kind of an important question, actually. Like as you're designing motors and engines and stuff, you want to know the torques that are being applied, and you have various braking mechanisms. You need to know, what the force is required to make those things stop in a certain displacement. How would I approach this problem? Well, I know the work required, right? That I'm required to have 50 joules of work. And I also know that work is not force times distance, remember. It's tau times theta, my torque times my angular displacement. And so I can calculate now what is theta. First, I need to calculate what is the torque. That's going to be force times the, let me get rid of that d, not fd, fr sine theta. So that's going to be a half of a Newton times this distance, which is the radius. What's the radius of this hoop? Oh, it's 1 meter. Times the sine of 90. And that's equal to a half a Newton meter, or half a Newton meter. Okay? So now I can figure out what is theta. I can say that the work is 50 joules equals to the torque, which is a half Newton meter, times theta. And then I would solve that for theta. Theta would be equal to 50 divided by a half, which is 100. What are the units for theta in this case? I've been dealing with SI units, so what must the units for theta be? Radians, right. So the units for theta are going to be in radians. And so then, because I asked for it in revolutions here, you'll need to convert that to revolutions. 2 pi radians, 1 revolution, 100 divided by 6 is about, what? What is that? Savannah, do you know what it is? Okay, about 16. Maybe not quite that, but about that. That's revolutions. Okay? We could have approached that in different ways. Like we could have found out what is the torque, and then find out what is the angular acceleration, and then figure out, okay, that angular acceleration with this initial velocity, how long is it going to take to stop, and then what is the angular displacement in that time for it to stop. But just like we saw in Chapter 6, that problems become a lot easier when you approach them from an energy perspective than they do from a kinematics and a Newton second law perspective. They're often a lot easier to deal with. Okay, let's try this problem. These are good test questions, all of these. "23 people. Feel free to ask your neighbor what they put, okay? Or how they're approaching the problem. All right, let's stop in about 15 seconds or so. Stop at 3:05. 3:05. Okay, there are a number of steps that you have to go through on this. The first thing that you need to do is just figure out what is the moment of inertia. And so we'll start with that. We'll say the moment of inertia, and you look back at your little table and look for the right one. And then you have to figure out, well, this is a spinning disk, so that's like a flat cylinder, and the moment of inertia for a cylinder is 1/2 mr squared. Okay? So remember, if we have a spinning disk, that's just a cylinder that rotates about that axis that goes down through the middle. Half of the mass, that's 100 kilograms. times the radius is 1 meter. That's squared. And so the moment of inertia is 50 kilogram meter squared. Let's do that right off the bat. You'll have some problems where you have to just outright calculate the moment of inertia, but most of them will be part of a bigger problem like this one. So we have that off to the side. I'm just going to sort of put a box around it. Now, I need to figure out the torque. Because really what I'm trying to get to is how fast is this thing spinning now? And in order to know how fast it's spinning, then I need to know what is the force that's being applied to it. That is the angular force, or the torque. All right? And then I'll be able to figure out the acceleration, and then I'll be able to figure out the velocity. All right, so the torque now is force times r times sine of theta. That's going to be our force of 50 newtons. It's applied tangentially. What that means is that our angle is 90 degrees. 50 newtons at a moment arm of 1 meter times sine of 90. So my torque is 50 newton meters. Let me say something, just in case you picked up on this. I'm not sure if you have. You probably don't remember. But back in chapter 5, when we were talking about work, I said that the units for work are newton meters, but I like to use joules. This is the reason I like to use joules, because the units for torque are also newton meters. But this is different from work. Right? Work is force times distance. And similarly, torque is force times the distance. But these are different quantities. They're not the same units. Okay? But just in case you see this elsewhere, you might see that pop up. Newton meters, if you've ever used a torque wrench is measured in newton meters. Or sometimes they're in, what are they in? Anybody know? On a torque wrench? They're in foot-pounds, right? Often, because we're in the British system. Okay, so now that we know the torque, I know that our torque is equal to I times alpha. That's Newton's second law. So my acceleration then is going to be torque over I, which is going to be 50 over 50. Which is equal to 1 radian per second. And now if I want to know the angular speed, that's going to be omega. Omega will equal to omega naught plus alpha t. Omega naught is 0. Just a second, Mallory. So alpha is 1 radian per second squared times 3 seconds, so it's going to be 3 radians per second. Okay, the units, thank you. Okay? You're certainly going to see some questions like this on the test, where you have to go through this process. I know there are a bunch of steps, but they're the same steps that we've done before. You're just dealing with slightly different equations with the Newton's second law of distance. Okay? A lot of equations in this chapter. That's why I gave you an equation sheet. And in a minute, I'll recap everything to sort of put it all on one page for you so you can see it. Let's look at our last thing, which is angular momentum. So remember, in this chapter, we're sort of recapping every chapter that we've had so far, but putting everything into a rotational frame. The angular momentum, just to remind you, before we dealt with linear momentum. Linear momentum was mass times velocity. It was a vector quantity, and this one will be a vector quantity too. The angular momentum is the product of the moment of inertia and the angular velocity. All right, we're going to write angular momentum as L. I'm not sure why we use L. I think because P is already used a lot. Well, no, angular momentum doesn't start with P. I don't know why we use L. We just use L. Anyway, L is equal to the moment of inertia times omega. These are vector quantities, but they're sort of funky vectors. We get into that right-hand rule that we used last time, so we're not going to worry so much about the direction of them, but we will worry about what direction are the things spinning. So we'll sort of talk about the direction in terms of clockwise or counterclockwise, though as you know, that's not really the direction of these vectors, that these vectors are actually perpendicular to the spinning surface. Remember the right-hand rule that your fingers fold around, and then the angular speed is actually perpendicular. We'll see that again next semester, so don't sweat it too much right now. But again, we can compare this with our expression for linear momentum, P equal m times v. The SI unit is kilogram meter squared per second. And just like we saw before with linear momentum, angular momentum is going to be conserved. So Li will equal to LF. And usually we're just going to have one thing that's being changed in the system, whereas before we had collisions between objects. We might see a collision of sorts, but usually it's going to be that we're bringing two objects together. I'll work through an example and show you. Well, let me just write this out. Li is I initial, omega initial, is equal to I final times omega final. And so if I expand these all out, mr squared omega initial is equal to mr squared omega final, I can see how changing some of the variables will change other variables. So for example, let's say that I make my mass go up. So say if the mass goes up over here, then that's going to mean that the angular speed will go down. If I increase the mass of a spinning object, then it's going to slow down. Or if, for example, I make the radius of the object go up, then the speed will also go down. Right? You ever seen the figure skaters that go out? Cheerleaders and gymnasts and stuff, they do this a lot too, where they use their body to change their moment of inertia, and it changes how they spin. But if you've ever seen the figure skaters, they'll be spinning really fast, and then they'll throw their arms out. And when they do that, they're increasing their moment of inertia here by increasing R, and then that's going to cause their omega to go down. All right? Okay? All right. We'll look at some examples of how this works out. Let's actually go into the workbook, and we'll into your practice problems, and we will work through an example, and then we'll come back to that. Let's go to this one, number 7. All right, so here I have these 4 objects. These are spinning masses. They're spinning about this axis, and they're spinning around in this direction. And the distance between the axis of rotation is 1 meter for each of these objects. And then I want to know what happens to this thing. It's initially spinning at 2 revolutions per second. I want to know what happens if the spokes are shortened by 1/2 meter. And so what I'm going to do is, I'll say that Li is equal to Lf. That is I initial, omega initial, is equal to I final, omega final. I initial is going to be the sum of mr squared. I know that I do this because it's not one of our regular shapes, that it's actually a particle that is rotating about a central axis of rotation. And so I'm going to treat this like a collection of particles. So it's the sum of mr squared times omega initial plus are equal to sum mr squared omega final. And now I can start putting in some numbers here. The masses of these guys were... What is the mass? Oh. Well, turns out it doesn't really matter, so I'll just leave the mass out. Actually, you can see that here, because the masses just cancel here. That is really all that's important, since we have the same mass from beginning to end, is that the distribution of the mass is changing. So I have r squared, which is going to be 1 meter squared, times 4, because there are 4 of them, times omega I, which was 2 revolutions per second. And before you answer this, think to yourself, is this thing going to speed up or is it going to slow down? As these masses move in closer, what's going to happen to it? Is it going to speed up or slow down? It's going to speed up. It's like your figure skater. Right? And she starts spinning faster. It's because she's changed her moment of inertia. This is going to be 4 times 0.5 meters squared times omega final. Just set back here. Let me point out what I've done here. The masses cancel, right? So this 4 that I wrote here isn't from the mass. What is the 4? Because there are 4 particles. Right, it turns out actually that these 4s are going to cancel out too. So even if you forget those, it's not that important. So the 4s cancel, and then I solve for omega f. That's 2 divided by a half squared equal omega f. That's 2 over a quarter, which is 8. So omega final is equal to 8 revolutions per second. Notice that I didn't convert my omega to radians per second. That I can keep it in these non-SI units. It just means that my answer is going to come out in non-SI units. It's kind of like what we did with kinematics. And that's why we could do that with kinematics, because the units all worked out in the end. And that's true for angular momentum too. It's not true for anything else, only with the kinematics equations and now with this angular momentum. Okay? Nothing else. All others you have to convert to radians. And in fact, if you're confused, just always convert it to radians. All right, but that's going to be the answer there. You'll get the hang of it as we work through problems. Let's try that clicker question back up a bit. By the way, you'll have an OpenStax. It's going to be a doozy again, okay? But it's good for you. A lot of them are sort of quick questions. They're conceptual. The calculations are going to be easier calculations, and they'll be more in line with what you'll see on the next test. So it's a good thing to have a long test, a long OpenStax assignment. I'll be posting it this afternoon, and it'll be due next week sometime, Wednesday, I think. Let's try this one. In this one, you have a merry-go-round, and it's spinning at a certain speed, and then you get a kid that jumps onto the edge of the merry-go-round. And so now you need to think about, how am I going to treat the moment of inertia for this system? I know how to find the moment of inertia for a merry-go-round. That's easy, right? But what if I get a kid that jumps onto the outer edge of the merry-go-round? All right? You can also, it's spinning at 2 revolutions per second. You can probably imagine what the answer is going to be and maybe eliminate some of the possible options that I've given you. Let's do about 10 or 15 more seconds. Stop at 2:30, 2:30. 10 more seconds. Doing pretty well. 230. Okay, so first I want to figure out what is my initial moment of inertia. I initial for a disk is 1/2 mr squared. That's the spinning cylinder. I like the spinning cylinder, don't y'all? But you can see any sort of shape. You can see a spinning bar, spinning sphere, and likely you'll see some different shapes on the test. 1/2 mr squared, it's a half of 100 times 1 squared, that's 50. Let me write it out. 1/2 of 100 kilograms times 1 meter, that's the radius, squared, that's 50 kilogram meter squared. Is that somebody yelling? Is it like some professor, you think? Do they yell at you? They yell at you? Who does? I had a band directors, man, they are crazy. Crazy band directors out there. I don't know what it is, but in junior high, she would throw chairs. Like, not at us, fortunately, but she would throw them. She was a very good flautist. Is that a person that plays the flute? Is that a flautist? Flautist, yes. She was very good at playing the flute. Okay, so I initial is 50 kilogram meter squared. And now we need to figure out what is I final. Well, I know it's going to be 50 plus something, right? Because when I add this kid onto the merry-go-round, the moment of inertia increases. How am I going to treat that kid? What kind of shape am I going to treat that kid like? No! No! Not as a cylinder. You sound so confident. I'm sorry to beat you down. Think of the kid as a particle. You'll see this on the OpenStax, actually, because I picked a problem where you have some shape that's spinning around in a circle, and you would think, oh, I'm going to use the shape. But no, you're not going to do that. You're going to use it, because it's spinning around an axis, you're going to use it as a particle. So this kid, we just imagine as a particle on the edge of this. So the moment of inertia of the kid, you can imagine as the kid is just a particle that's going around in a circle as mr squared. So the kid has a mass of 50 kilograms times the radius, which is 1 meter, squared. All right, so that's 100 kilogram meter squared. Let me go back to this. So we're sort of just approximating this kid as being a particle of mass on the edge of this spinning cylinder. I understand why you'd say that we would approximate the kid as a cylinder. In fact, we did that before, right, with Richard Pryor? But that was different, because then Richard Pryor was rotating about this axis. And so we had to figure out what was his moment of inertia about that axis. Or you might approximate a person as a cylinder about this axis, rotating around. But here, this is different, because he's not rotating about any axis on his body. Instead, the entire body is rotating about a central axis. And in that case, anytime you have any body rotating about a central axis, you're going to treat it like this, m times r squared, just as a particle. And in that case, we sort of forget about the shape of the particle. And instead, we just treat it like a point source, a point mass. Okay? Y'all with me on that? It comes up on OpenStax too. You have a similar problem. It's just, what is the moment of inertia of the system? But you're going to be compelled to treat it like whatever shape it is. I forget what it was. But that's not really the case. It's actually rotating about a central axis, and so you treat it as a particle. Okay, so that's I final. And now we look at our momentum. Li is equal to Lf. I1 omega, or I initial omega initial, is equal to I final omega final. That's going to be 50 kilogram meter squared times 2 revolutions per second. Remember, I can keep it in revolutions here. And I final is 100 omega final. All right, since my moment of inertia has gone up by a factor of 2, my angular velocity is going to go down by a factor of 2. So it's going to be equal to 1. see what y'all put. Okay, that's all right. 85%. Okay, people. Let's do some more clicker questions. I think that's the end. Let's do some. Oh wait, no! Don't turn back yet. Let me just sort of recap this whole chapter right now, just to help you get it straight in your brain, because there's a lot of stuff in this chapter, in chapter 8. I'm just going to sort of recap with the equations, okay? So first, we dealt with torques. Remember, torque is equal to Fr sine theta. So if I have an object that's spinning about this, my force is here. This is my angle, or this is my arm, my moment arm. It's not a radius, it's a moment arm. And then this is my angle theta. Often that angle theta is 90 degrees. Remember, clockwise torques are negative, counterclockwise are positive. And then after torques, and the balancing of torques, oh, and by the way, this comes up in your OpenStax. We talked about this. We can have two rules for stability. That is, the sum of the forces have to be 0, and the sum of the torques have to be 0. And both of those have to be true if an object is not moving. Okay? We saw moment of inertia. For a particle, it's the sum of mr squared for a collection of particles. But if we have shapes, they come from that table that we've derived. Then Newton's second law. Torque is equal to I times alpha. These are vectors, but we haven't really been treating them as vectors, but that's okay. So torque is equal to I alpha. So when we find our net torque, we can determine what is the angular acceleration of that object. And then kinetic energy is 1/2 I omega squared. And remember that the total energy is equal to the rotational kinetic energy plus the translational kinetic energy. There's a problem in the workbook where you have to just calculate what is the total energy, adding up the translational and the rotational kinetic energy. And then finally, our momentum, L is equal to I times omega, and then also that this is conserved. Li is equal to Lf. You don't have to memorize those equations. Those equations are on your equation sheet. But I find it useful just to put them all in order here, and sort of in the order that you'll see them on the exam. Okay? It's a little more difficult chapter, chapter 8, than what we saw before. But I think you'll find the next chapters are less so. But if you've been doing well, it's a lot like what we've been doing. It's just sort of easier version of what we've been doing. But different with rotation. It's sort of I don't know, it's a toss-up. Okay, let's do some clicker questions. We know with the figure skater that when she pulls her arms in, the moment of inertia goes down, right? And so that's why she spins faster, because I goes down, omega has to go up by the same amount. So if she decreases her moment of inertia by a factor of 2, then omega has to go up by a factor of 2. And so now this is asking, what happens to her kinetic energy? Is her kinetic energy now going to be the same, right? Or is it going to be larger because she's rotating faster, which is true, she is rotating faster. Or is it going to be smaller because the rotational inertia is smaller, which is also true. The rotational inertia is smaller. So which is it? Is the energy the same, larger, or smaller? And remember, let me just recap what I said. That I know that L is equal to I times omega, and that this remains constant. When she brings her arms in, this goes down, so this goes up. So then what happens to her kinetic energy? I goes down and omega goes up. What happens to her kinetic energy? I'm going to stop at 1 35, 135. Okay, good. B is right, though I appreciate A, because A seems like it should be right, because we talked about the whole conservation of energy, how energy is conserved. And it doesn't seem like there are any outside forces acting on her, right? And so how can she have this increase in energy if there are no outside forces acting on it? We'll come back to that. That's like a mystery of the universe. But we'll come back to it in just a second. But first, let's think about the kinetic energy. Kinetic energy is 1/2 I omega squared. So let's say that I goes down by a factor of 2. So I get this factor of 1/2 here in I. That means that omega is going to increase also by a factor of 2. Y'all follow what I'm saying? Momentum's always conserved. And so if I goes down, omega's going up. That has to happen. It always happens. So if this goes down by a factor of 1/2, just say 1/2, that means this is going to go up by a factor of 2. And so I get 1/2 right here, but I get a 4 right here. So actually my kinetic energy is going to go up by a factor of 2. Because the omega is more important in this equation. It dominates that equation because it's a quadratic term, it's squared. And so whatever I do here is squared. So since omega is increasing, my kinetic energy is going to get bigger too. So have y'all thought about where that extra work comes from? Or are you still puzzled about it? Like, why does her energy increase? There has to have been work that was done on her in order to increase her energy. No, I'm not even going to tell you. I'm just going to make you go the rest of the day wondering. You don't know where it comes from? Her arms, right? When she pulls her arms in, that's exerting a force over a certain distance, and it's actually bringing force or bringing work, energy into her system. Okay, 2 spinning disks have the same angular momentum, but disk 1 has more kinetic energy. Which one has the bigger moment of inertia? This question always gives me a headache. Which one is it? The product of I and omega are the same for both, but disk 1 has more kinetic energy. All right. About 15 more seconds? Or 10 seconds? Stop at 53. 53? Okay, B is right. The one with the bigger moments of inertia, I and omega, this product is the same. The one with the bigger moments of inertia is going to be the one with the smaller angular velocity. But the one with the smaller angular velocity is going to be the one with less energy. And the one with less energy is disk 2. It's similar to what we had before, that it's 1/2 I omega squared. And so omega dominates the energy. Okay, let's do this and then we'll be done. What happens to these as rain falls into these rotating buckets? You start dropping water into these rotating buckets. What happens to them? And why? All right, ask your neighbor. Almost everybody has the right answer. So if you're uncertain, ask the neighbor next to you. All right, just a few more seconds. 48, I'll stop. Okay, good. Wait, hold on. So, as you drop water into the buckets, the mass increases. That increases I, so omega has to go down. Where does an astronaut go to hang out? The safe spot. Bye, y'all. Have a good day.
Savannah, it's just a thought.